Yeah, welcome to today's session. In today's session, what we do is we'll go through the topics, characteristic roots, or popularly they are called as eigenvalues, and another one is characteristic vectors, or another name for it is eigenvectors. That means eigenvalues and eigenvectors of a matrix, followed by Cayley-Hamilton theorem. Okay. So this is the agenda for. So this is what we are going to see in today's session. Okay. Just a minute, I will check the noise. Followed by Cayley-Hamilton theorem. So we'll go through the introduction. So what is this eigenvalues and eigenvectors? So other name is also there, that is latent roots and latent vectors. Okay. So actually it is eigen means I think it is a German word which means characteristics. Right? So that means it helps us to understand the characteristics of a matrix. Right? So that's why we are calling it the concept as characteristic roots, characteristic vectors, or eigenvalues, or eigenvectors. So what is the importance, or what is the use of these terms or this topic? Actually, this is having this topic is very important with respect to applications. Particularly important applications which people have been talking now is principal component analysis. So which is one of the popular term as a pre-processing of data in data science or machine learning kind of data science, data mining or machine learning kind of courses. So this PCA is popular because it is one of the dimensionality reductions techniques. Right? So it helps us to reduce the dimensions of the data given. Right? So that means here it helps us in compressing the data. Right? So why we need to compress data? If it is having many features, then building a model over the data given is complicated. So what we feel is if it is having less features, then it is very easy to understand, even very easy to visualize the data also. Right? So what we do is we want to see what are the important features which are useful in analyzing the data or modeling the data. Okay. So here to be more clear, suppose if you take a data related to the salary, suppose we were building a model where we had salary of employees in an organization, right? So where salary, the service, qualification, their height, male or female, date of birth, etc. Many are there in the data, right? So now, so we want to find out what are the important features or the uh, components which are very important where we want to build a model related to salary, right? That is, what is the important feature which affects the salary, right? So to understand, that means here it is having many dimensions, 1 2 3 4 5 6 7, right? We want to reduce it to 2 dimensions or 3 dimensions so that it becomes very easy for us to build a model. So that is what we call as dimensionality reduction, right? So how we understand is, actually that we are not going to discuss. That is a topic in length where people go through clearly when they go for data mining or machine learning of kind of courses where they talk about pre-processing of the data, where this is one of the important. So here in dimensionality reduction, so that is by using PCA, eigenvalues, eigenvectors plays a crucial role. That is the importance of eigenvalues and eigenvectors. So here some observations. The eigenvectors are called as principal axis or principal directions of the data, or principal components they are called as. So in general, almost all vectors change the direction when they are multiplied by A. But certain exceptional vectors x are there which won't change the direction, they continue in the same direction as x. So those are called as eigenvectors, right? And when multiply an eigenvector by a, then the vector ax is the number of lambda times of the original length. That means what it says is, so then it becomes ax equal to lambda x. Right? So actually the other way what we define is, in general when we talk about matrices is nothing but matrix consisting of column vectors, right? So now when we talk about the vectors will have, when we talk about vector, two kinds of terms we use. One is rotation and scaling, right? So if I take a vector, right? So most of the applications what we look for is, so how far we can stretch or compress the vector and the rotation, right? So when we talk about the stretching of a vector, right? So there the eigenvalues and eigenvector concept comes into picture, right? So the eigenvalues and eigenvectors helps us to understand how much we can stretch and in which direction we can stretch, right? So that those two things will have from lambda as well as x, right? So that is one of the physical significance of the eigenvalues and eigenvectors. That is stretching of vectors, how much we can stretch and in which direction we can stretch the vector. So those two things are explained by eigenvalues and eigenvectors respectively. Okay, so then that is the brief introduction and what is the importance and where we apply. Now coming to the mathematical aspects of eigenvalues and eigenvectors. So we'll go through one by one clearly. So first term is here characteristic equation. So what is this characteristic equation? Suppose A is a square matrix of order n, right? A is a square matrix particularly of order n. Then if we take a matrix A minus lambda I, lambda is some constant or scalar, and I is the identity vector, corresponding identity vector means if A is a square matrix of order 2, then we have to take identity matrix of order 2, right? So this matrix A minus lambda I is a matrix, right? So for every square matrix we can have this A minus lambda I. Suppose if we take data of this matrix, right, determinant of this matrix, that is data of A minus lambda I, and if it equate to 0, then this is called as characteristic equation of A, right? So for a square matrix of order square matrix A of order n, data of A minus lambda I equal to 0 is called as the characteristic equation. So in general, if we expand this, what we get? Right? Suppose if it is a 2 by 2 matrix, right? Some matrix 1, 2, 3, 4. Right? If we take this matrix, then we'll get corresponding polynomial. That is, if it is a 2 by 2 matrix, we'll get some lambda square plus constant into lambda plus the constant equal to 0. If it is a 3 by 3 matrix, then we'll get a polynomial of order 3. Right? Like this, we'll get the characteristic equation. Okay. So like this, suppose det of a minus lambda equal to 0. Now we took the general matrix a11, a12, a1n. Right? This is the matrix. Minus if we take lambda into I. So if I is the identity matrix, right? One identity we know it 1 0 0, right? 0 1 0. Suppose if I take 3 by 3 identity matrix, 0 0 1, right? Suppose if you multiply this by lambda, only the only the diagonal elements varies, right? Lambda, 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 then a minus lambda. That's why you can see here a11 minus lambda, that is a diagonal element, a22 minus lambda, so on ann minus lambda. Now if we expand this, right? If we expand this determinant, right? So then we'll get a polynomial of order n. This is what that is. Right? Polynomial of order n, minus 1 power n lambda power n k1 lambda power n minus 2 and so on equal to 0. So where k1 k2 are nothing but, so depending on the expansion, so k1 k2 are nothing but the addition or subtraction or the combination of a11 a22 a12 a13, like ai's aij's a11 a12 a13 and so on, right? So this is what is characteristic equation and how it looks like. Okay. Now the basic way that we define eigenvalues and eigenvectors is, if there is a matrix A, right? If there is a matrix A, and there is a column matrix or column vector X, and there is a scalar lambda such that Ax equal to lambda x. Right? So A is a matrix and X is a column vector or column matrix and lambda is a scalar such that Ax equal to lambda x. Right? So then this lambda is called as eigenvalue of A, and this x is called as eigenvector of A corresponding to this lambda. That means here actually for every lambda we'll have a corresponding x. Right? So that is the basic definition of eigenvalue and eigenvector is in another sense. So now the question comes how to find, right? How to find the arrangement of lambda and x such that Ax equal to lambda x. Right? So that we'll see. Now from the definition what we are saying, Ax equal to lambda x, right? So now lambda is a scalar, right? Or constant, what we say, right? Lambda is a constant or a scalar, right? So here if lambda x is a column vector, right? So we can write, without loss of generality, we can write this as lambda into I into x. So that is Ax equal to lambda Ix. Now we can write this as, by taking x common, so we can write this as a minus lambda I into x equal to 0. A minus lambda I into x equal to 0. So we know this is a matrix, right? A minus lambda I is a matrix, that's some matrix, into x equal to 0. We know this is nothing but system of homogeneous equations, right? So once we say system of homogeneous equation, already we discussed in the earlier sessions. So it will have trivial solution, non-trivial solution, right? So only we try to find non-trivial solution. That condition for non-trivial solution is det of the matrix equal to 0, right? So that is det of A minus lambda equal to 0. So this system of equations will have a non-trivial solution, that means x. So when det of A minus lambda equal to 0. So this already what we have seen, right? This is nothing but characteristic equation of the matrix A, right? Now, how to find eigenvalues, eigenvectors is, now this is a polynomial as discussed, right? Depending on the order of the matrix, we'll get a second order polynomial or third order polynomial. So if we solve the polynomial, we'll get the roots of the polynomial, which are nothing but eigenvalues, right? That is lambdas. So once we had lambda, if we put lambda here, right? If we put lambda, then it becomes a system of homogeneous equations. When we solve this system of homogeneous equation, we'll get its corresponding x. X means nothing but its eigenvector or characteristic vector, right? So that means for each lambda, we have to solve the corresponding system of equations to get corresponding eigenvector. Okay. So before solving one problem, we see two definitions related to eigenvalues. One is algebraic multiplicity of lambda, other one is geometric multiplicity of lambda. So what is this algebraic multiplicity of lambda? If lambda is characteristic root or eigenvalue of a matrix which is of order t, right? So then the t is called as algebraic multiplicity. Suppose if S is the number of linearly independent eigenvectors for a given eigenvalue, we'll find eigenvectors, right? Then the number of linearly independent eigenvectors corresponding to that lambda, which is denoted by S, is called as geometric multiplicity of that eigenvalue. Okay. So order of the corresponding characteristic root is algebraic multiplicity. The number of linearly independent eigenvectors is geometric multiplicity of corresponding eigenvalue. Right? Okay. Now we'll see with one example to understand this concept clearly. So one is find the I think regularly wherever this topic is there in any exam, this regular question. So find the eigenvalues and the corresponding eigenvectors, right? Here in this now we'll discuss wherever we will have eigenvalues. For each eigenvalue we'll discuss its algebraic multiplicity as well as geometric multiplicity. So now, so here A is a matrix of order 3 by 3. Right? So immediately what we remember is we'll get a third order polynomial. That means we'll get three roots, that means 3 eigenvalues. For each eigenvalue, we have to find an eigenvector. That means we'll have 3 eigenvalues and corresponding 3 eigenvectors. If there is any repetition of eigenvalue, then it is a different story. So only once we solve, and from that we'll have the eigenvector corresponding. Okay. Now, as discussed, first thing what we have to do is what is this characteristic equation and polynomial. So first characteristic equation of A is det of A minus lambda equal to 0. So that is nothing but only from the diagonals elements we have to take minus lambda, minus lambda, minus lambda. Rest remains the same in the determinant, right? So here you can observe. So 8 minus lambda, 7 minus lambda, and 3 minus lambda. So now we have to expand. This is a determinant. So we have to expand the determinant. So we have seen several times and we know how to expand. So we are expanding this along first row. So 8 minus lambda into 7 minus lambda into 3 minus lambda minus of minus 4 into minus 4. That is minus 16. So next second element is minus 6 minus of minus 6 and minus 6 into 3 minus lambda minus 4 into 2. So this is next third one 2 into, so leaving that same what we discussed in a minute, minus 6 into minus 4 minus 2 into 7 minus lambda equal to 0. Right? So like this we have to expand the corresponding eigenvalue as well as eigenvector, right? We have to expand the this determinant. One minute. So we have to expand the the determinant, right? So then if we expand the determinant, what we get is, in this case, if you go further, so it is lambda cube minus 8 lambda square plus 45 lambda equal to 0. Simply what we have done here is we just simplified, we multiplied this and simplified. So then we got this lambda cube minus 18 lambda square plus 45 lambda equal to 0. So now next step is we have to find the roots of this equation, right? So we have to find the roots. Here in this case, very simple. If you take lambda common, then lambda square minus 18 lambda plus 45 equal to 0. So lambda equal to 0 is one root. Then lambda square minus 18 lambda plus 45. Then we have to factorize this. So we have to solve this by maybe using minus p plus r minus under root of b square minus 4ac by 2a or factorization. In this case, very simple. 15 threes or 45, 15 plus 3. So lambda square minus 3 lambda minus 15 lambda plus 45 lambda, if we take the common, lambda minus 3 minus 15, if we take common, lambda minus 3. This is a simple school mathematics what we are familiar with. Okay. So then it is lambda minus 3 into lambda minus 15 equal to 0. Therefore we got 3 values for lambda, right? Lambda equal to 0, 3, 15. So if you remember, the order of the matrix given is 3, so we have to get 3 eigenvalues. We got 3 eigenvalues. So now actually the later part will discuss some of the properties which helps us to understand eigenvalues. Or otherwise, time being, we can whenever we solve the characteristic equation, whenever we will have eigenvalues, then we have to validate it. We can validate whatever we got or right or wrong. One simple thing is, so see what is the sum of eigenvalues. Right? So here 3 values are there, right? Sum of the eigenvalues 0 plus 3 plus 15, 18, right? Then go back to the matrix. So what is the sum of diagonal element, that is trace what we call as. So this is a diagonal, right? So what is 7 plus 3, 10, 10 plus 8, 18, right? That is a trace of the matrix or sum of principal diagonal elements in the matrix. 7 plus 3 plus 8, 18. And here, if you see the sum of eigenvalues, 0 plus 3 plus 15, 18. So same, that means we can say that whatever we are having are right eigenvalues, right? Like this, we are having some properties. By using those properties, whenever we want, we can validate. Okay, clear? So now, once this is done, then what we have to do for each eigenvalue, for when lambda equal to 0, we have to find what is x, right? So when lambda equal to 3, we have to find x. When lambda equal to 15, we have to find x, right? So how to find, right? So then we'll go back to our original matrix A minus lambda I into x equal to 0, right? So this is the matrix here. So now we are doing this for lambda equal to 0. So put lambda equal to 0, right? So then this. So now this is A x equal to 0, Ax equal to 0. Now if you remember, this is nothing but the system of homogeneous equations, right? So we have to solve this homogeneous system. How to solve? So I think in the previous sessions what we discussed, right? So we have to first convert this into echelon form, right? So by using appropriate row operations, then we'll get the rank of the matrix, then number of variables, then we'll compare it. From that we'll say whether it will have trivial or non-trivial. This is what we discussed. But here, so always it will have non-trivial. Only thing is here in this case, whether rank becomes 2 or rank becomes 1 is the question, right? It never becomes rank as 3. If rank becomes 3, number of variables 3, that means only trivial. No, because here we are having lambda values where there exists non-trivial solution. So that's why that case won't come into picture, right? So this is one of the important points. Now, so what we have to do is we have to go for row operations. where we have to convert this into echelon form, right? So this is a principal diagonal, right? So where we have to make this as 0, this as 0, right? Same like what we discussed in case of solving system of equations. So appropriate operations, right? Here 4 into R2, 3 into R1, and here 4 into R3 minus R1. So then we got this. So now again we'll check. So this is our principal diagonal, right? So whether we got echelon form or not, no, right? So minus 10 is there, right? So we have to make this as 0. So where the operation is R3 equal to R3 minus R2. So now we got this, right? So this is echelon form, right? So we can verify it. Sorry. So this is the principal diagonal, right? This is the principal diagonal. So elements below it 0, 0, 0. Right? This is an echelon form. And next immediately comes what is the rank of the matrix? Number of non-zero rows, that is 2. Number of variables 3. Obviously it will have a non-trivial solution. Right? How to have the non-trivial solution? Same like we have to rewrite this matrix in terms of equations. 8x1 minus 6x2 plus 2x3 equal to 0. Right? Second one, this is x1 is 0, 10x2 minus 10x3 equal to 0. So that is 3 variables and 2 equations, right? 3 variables x1, x2, x3, 2 equations. That means our solution contains one constant, right? So here how to solve it? Choose either of these. Here in this case very simple, 10 gets cancelled, x2 equal to x3. Suppose if we take x2 equal to k, x3 also becomes k. If we substitute x2 equal to k, x3 equal to k here in this equation. So from this we'll get x1 value, x1 equal to k by 2. That means we got our eigenvector, first eigenvector corresponding to lambda equal to 0, which is k by 2, k and k. Now, as discussed many times, non-trivial solution is nothing but infinitely many solutions, right? By giving various values to k, we can have many eigenvectors. So here suppose take k equal to 2, then we'll get 1, 2, 2. Right? So any value we can take so that we can have corresponding eigenvector. Okay? Now, so before going for the second eigenvector, so we'll see the multiplicity corresponding to this. So here we got this as the eigenvector, right? Eigenvector. So now rank of A is, if we go back and see, this is A, right? Just now we discussed rank of this matrix A is nothing but number of non-zero rows, that is nothing but 2 only, right? The rank is 2. And order of the matrix. So given matrix is of order, square matrix of order 3. So then the number of linearly independent eigenvectors are n minus r. So 3 minus 2, that is 1. So then we have to say what is the algebraic multiplicity and geometric multiplicity. Algebraic multiplicity is 1. Right? So the what degree of the eigenvalue is 1. Therefore, algebraic multiplicity is 1. So geometric multiplicity is also 1 because it contains a number of linearly eigenvectors as 1. Right? So therefore, algebraic multiplicity is 1. Geometric multiplicity is also 1. So like this, whenever it is asked, we need to find the both multiplicities corresponding to each eigenvalue here. Okay. Now, repeating the same process for rest of the 2 eigenvalues. Quickly we go through it. So now the second eigenvector is lambda equal to 15, right? Now simply here we replace lambda by 15. I say lambda 2 actually. So then we'll get this matrix, right? So immediately what we have to do is we have to convert this into echelon form, right? Same procedure like what we discussed in the case of first one. Right? So this is the principal diagonal. So we have to use appropriate row operations to make these elements as zeros, right? Okay. So these are the operations. So initially to reduce the larger numbers, divided by 2 and R3 by 2. These are what we got. Now making these as zeros. So by using this operation, R2 equal to 7R2 minus 3R1. R3 is 7R3 plus R1. Now just for the information, but check the rough work. These 7R2 minus 3R1, 7R3 plus R1 is also given here. We can go through it. So then after these operations, we got this matrix. So next still we have to go further to make this as a matrix which is in echelon form. So this is there, right? So then we have to go for an appropriate operation. So here R3 is R3 minus R2 because both rows are same, right? So the operation is R3 is R3 minus R2. Now we can see this is the echelon form of the matrix. So then number of non-zero rows 1, 2. Right. So rank is 2 less than 3, obviously non-trivial. That actually we did not check it. Right. So once we got this echelon form, obviously the rank has to be less than 3. It has to be 2 or it has to be 1. Depends on the matrix what we get. So immediately, so we have to rewrite the equations from this matrix. So minus 7x1 minus 6x2 plus 2x3 equal to 0. Second one, minus 10x2, 20x3 equal to 0. So same discussion, 3 variables and 2 equations. Therefore, our solution contains one arbitrary constant. So we can choose either of these. There is no restriction on it. So here in this case, we took it as x3 equal to k. Then from this x2 is minus 2k. Then if we substitute x2 and x3 here, right, so then we get 7x1 as 14k, x1 as 2k. That means we got x1, x2, x3. That means 2k minus 2k and k. Suppose k, take k equal to 1. Smallest value for k, like this. Any value we can take because for what we are saying, it contains infinitely many solutions, right? So it need not be the same for everybody. Right? So here I took k equal to 1, then this is one eigenvector corresponding to the eigenvalue lambda equal to 15. So then we'll discuss the multiplicities. Here I think it almost similar kind of discussion because there is no variation in terms of the eigenvalues as well as eigenvectors. So rank is 2, order is 3, number of linearly independent eigenvectors n minus r. N is number of variables or order of the matrix given. What is the order of the matrix A given? Right. So minus r is rank of the matrix A what we had. So 1. So multiplicity. So the degree of this eigenvalue is also 1. Therefore algebraic multiplicity is 1. Similarly geometric multiplicity. Geometric multiplicity is nothing but this. The number of linearly independent eigenvectors corresponding to this eigenvalue. Right. Okay. So next one more left. For I think quickly we go through because the process is same, only you need to practice it. Okay. So lambda equal to 3. So we replace lambda by 3 here, then we'll get this matrix. Right. So then same process. So this is principal diagonal. So we have to make these elements as zeros. Right. By using appropriate row operations only. Repeatedly I have been telling, we have been discussing. So only row operations, no column operations. Right. So some operations we as shown here, R2 is R2 minus 2, R3 is R3 by 2, then this matrix. Right. Then so to make these elements as zeros, the corresponding operations are R3, this one and this one. So here the rough work is corresponding to these operations is shown here. You can go through it. Okay. So after these operations, this is what we are getting. Okay. So still one more left. So we have to go further with one operation are required more operations to make this as a matrix which is of the form that is echelon form. Right. So So after the operations and everything, this is the matrix what we got. So we can verify it. Is it in echelon form or not? Yes, it is in echelon form. Then rank is same discussion. Rank is number of non-zero rows, that is 2, less than 3, that is number of variables, non-trivial. So as discussed, there is no need for us to check whether trivial or non-trivial kind of discussion here, because obviously it has to have non-trivial solution because of the condition what we imposed when we defined it. So now same process, we have to rewrite the equations from this 5x1 minus 6x2 plus 2x3. Here no x1, 0x1, so 2x2 and plus x3 equal to 0. So same three variables, two equations. So suppose x2 equal to k, then x3 is minus 2k, substituting here. So we got x2 as well as x3, substituting here we'll get x1. Right? So now we got third eigenvector as 2k, k minus 2k. So I took k equal to 1 here, then we got the corresponding eigenvector as this. Now same discussion here. So rank is 2, order is 3, then number of linearly independent eigenvectors 3 minus 2, that is equal to 1 as discussed many times. So here the degree of the eigenvalue is only 1, therefore here it is 1. Geometric multiplicity is not 3 mentioned here, it is 1 only. Same here. So n minus or n is number of variables 3. Rank of the matrix 2, 3 minus 2 equal to 1. That means it contains one linearly independent vector corresponding to this eigenvalue. So like this we have to find eigenvalues as eigenvectors in general. If required, we have to find the corresponding multiplicities, algebraic multiplicity as well as geometric multiplicity. So I hope that is clear. Right? So next is one of the important concept based on eigenvalues, eigenvectors, and in most of the examinations they will ask state and prove Cayley-Hamilton theorem, that is one statement, as well as proof of Cayley-Hamilton theorem. So second one, so they give you a matrix A and verify Cayley-Hamilton theorem for this matrix, and also find A inverse or find powers of A kind of thing. That is what generally appears in any examination. State and prove Cayley-Hamilton theorem, right? That is one case. Second case is for a given matrix, validate Cayley-Hamilton theorem and hence find A inverse. Right? So here we'll see it clearly. So statement is we'll prove the theorem also. So every square matrix satisfies its characteristic equation. This is the statement of Cayley-Hamilton theorem. We know characteristic equation, right? Already what we discussed, A minus lambda I equal to 0, right? For any square matrix A, this det of A minus lambda I equal to 0 is called as characteristic equation, which is a polynomial what we discussed. So here Cayley-Hamilton theorem says, so every square matrix satisfies this. You will see how it. Right? Quickly we go through the proof also, because many times for many of the examinations they'll ask this, state and prove Cayley-Hamilton theorem. Okay? So right. So proof is, let A be a square matrix of order n. Let A be a square matrix of order n. So then the corresponding, so 1 minute. So then let A be a square matrix of order n. Then this characteristic equation what we have been discussing is det of A minus lambda I, right? So if we expand this, already we have seen, right? In the previous case already we have seen, if you remember the case what we have taken. Right? So this is right. So this is a matrix of order 3 by 3, right? So then the characteristic equation is a polynomial of order 3 which is equal to 0, right? Lambda cube minus 18 lambda square plus, right? So matrix is of order 3, then this is of order 3, right? That is what we use here. That is what we mean. So that of a minus lambda I is, since it is a matrix of order n, then it is a polynomial of order n. So minus 1 power n lambda power n plus k1 lambda power n minus 1 plus so on kn equal to 0. So why this minus 1 power n is? So depending on the order of the matrix, if it is a square matrix, then it will be lambda square. Like if it is a matrix of order 3 by 3, then we'll have minus lambda cube plus so on like this. That's why it is minus 1 power n lambda power n k1 lambda power n minus 1 and so on equal to 0. Now, so what the Cayley-Hamilton theorem says, the square matrix A satisfies this equation. That means wherever lambda is there A, so we have to, whenever minus 1 power n, A power n, k1 into A power n minus 1 plus so on kn into I. So here it's only a constant, so without loss of generality we'll take, right? So if we say this equation holds good, minus 1 power n a power n plus k1 a power n minus 1 plus so on kn I equal to 0, that means what we are saying, so the matrix A satisfies this equation. That means the matrix A satisfies its characteristic equation, right? So that is nothing but Cayley-Hamilton theorem statement. So in order to prove the theorem, we have to prove this, right? So how to prove this, right? Next question. So this is one of the important and sometimes confusing also. So if we take the elements of the matrix A minus lambda I, so if we see the entries of this, right, they are at most of degree 1 in lambda, actually not n, degree, at most of degree 1 in lambda. Now if we take the adjoint of this, that means what we mean to say is, if we have seen the first one, right, it is 2 minus lambda, right? Here it is something like 4 minus lambda, right? 5 minus lambda, at like this, right? So remaining elements will be the constant without any lambda, right? This is the matrix. If we take the matrix here, this is for example, if we take a matrix like this, right? 2 minus lambda, 4 minus lambda, 5 minus lambda. So every element, if you see, this is at most a degree of 1 in lambda. It is not n, degree of 1 in lambda. Now if we take the adjoint of this, we know adjoint means, right, adjoint minus adjoint of this element. If we take 4 minus lambda into 5 minus lambda, right, it is a 3 by 3 matrix, therefore this adjoint will have in terms of lambda square, right? If it is a 4 by 4 matrix, we'll get lambda cube, right? So that is the important point here. If then the adjoint of A minus lambda I, which is nothing but cofactors of the elements of the matrix, and they represent a polynomial of degree n minus 1. So this is one of the important points and sometimes confusing point also, right? Okay. So that of adjoint of A minus lambda I, if you see this example, if you expand here 4 minus lambda into 5 minus lambda square, this is a 3 by 3 matrix, right? So we'll have lambda square at most, right? So 3 by 3 matrix, so here lambda square we are getting. 4 by 4 matrix will get lambda cube. So if it is a matrix of order n, then we'll get n minus 1, right? So then this matrix adjoint of A minus lambda I, generally denoted by P, so can be written as a matrix polynomial, right? So which is b1 lambda n minus 1, b2 lambda n minus 2 plus 1 bn, right? Okay, so I hope that's clear, right? So then we can whenever simple thing is, when a matrix is having polynomial as entries, now we can express it as a polynomial whose coefficients are matrices. That is the concept here, right? So by taking that lambda square terms out, then we'll have matrices like this. Right? So that's why this adjoint of A minus lambda I can be written as B1 lambda n minus 1, B2 lambda n minus 2, so on, Bn. It's a matrix polynomial actually. Okay. So with these two things, one point is det of A minus lambda I is this polynomial, that is first one, and another concept is one minute. So two things will carry to prove this. One is det of A minus lambda is a polynomial. This is a polynomial. This polynomial. And second one is the adjoint of A minus lambda I can be written as a matrix polynomial as B1 lambda n minus 1, B2 lambda n minus 2 plus 1, Pn. So again I repeat, because A is a matrix of order n, then B becomes a matrix polynomial of order n minus 1. So then we'll make use of this. So that is, we know A inverse, right? Already we discussed in the previous discussion also. A inverse equal to adjoint A by det A, right? So where if you cross multiply and if you multiply this expression through on both sides with A, then if you see here, I'll multiply this by A, then A into adjoint A. Here A into A inverse is nothing but I into A. So this comes. So A inverse equal to adjoint A can be written like this, where we pre-multiplication by A. Right? So this relation we use with respect to matrix A minus lambda I. Right? So instead of A, we'll take A minus lambda I. So A minus lambda I, adjoint of A minus lambda I, and det of A minus lambda I into I. Now A minus lambda I, the matrix as it is, and adjoint of A minus lambda I, as discussed just now, right? It can be written as a matrix polynomial, right? B1 lambda n minus 1, B2 lambda n minus 2, so on. And this is nothing but a characteristic polynomial, right? A minus lambda I, which is nothing but a polynomial of order n. Just now what we discussed, right? So this relation we use it for the matrix A minus lambda I, where we replace this adjoint of A minus lambda I by a matrix polynomial, and this det of A minus lambda I by its corresponding polynomial. So next this is, right? So this is what we have. Now what we do is we equate coefficients of equal powers of lambdas. So what we do is we multiply and we'll compare this equal powers of lambda. Suppose if we take the lambda power n, right? This side if you take, so if you take lambda I into B1 lambda n minus 1, right? Then lambda is there, lambda into lambda power n minus 1, that becomes lambda power n. Then what is its coefficient? B1 into I, right? This is, right? So this is coefficient of lambda power n in the left side. Right? So right side simply it is minus 1 power n into I. Right? Sorry. So similarly, if we take lambda power n minus 1, right? So what are the lambda power n minus 1 terms? One is this one, right? A into B1 lambda power n minus 1, right? So that is AB1. Second one is lambda into n minus. Now if you multiply this with respect to this term, AB2, right? Lambda B2 into lambda n minus 2, that means lambda power n minus 1. That's why this AB1 minus B2. This side it is simply K1 into I. Similarly, lambda power n minus 2, right? So what we have done here is, so we compared the similar powers of lambda. We took the coefficients. So this is lambda power n related, this is lambda power n minus related, this is lambda power n minus 2 related, and so on. So next what we are doing is, we multiply the first one by the matrix A power n, second one by A power n minus 2, A power n minus 2, and so on. So multiply both sides, first one by a power n, second one by a power n minus 1 and so on. Then what happens, you see here, this is a power n b1, right? And this side, this becomes a power n minus 1 into a, that is a power n b1. So these two terms gets cancelled, right? So then a b2 a n minus 1, right? When we go to the next step, this becomes a n minus 1 b2. These two terms gets cancelled. These two terms gets cancelled like this. All the terms in the left hand side gets cancelled. Then what we had left in the right hand side, if you see here, minus 1 into a power n, k1 into a power n minus 1, k2 into a power n minus 2, so on, right? That is nothing but minus 1 power n a n plus k1 into a power n minus 1 plus so on, kni equal to 0. So this is what we want to prove, right? If you go and see the statement what we mentioned. In order to prove, we have to prove this. In order to prove. So that is what we proved, minus 1 power n a power n plus k1 a power n minus 1 and so on. That means a is satisfying its characteristic equation. Right? That means we proved the Cayley-Hamilton theorem. So proof is very important. And in proving this, two important steps are, so this one is one important step, this is another important step, and this is another important step. Right? So we need to practice it to understand the proof of the Cayley-Hamilton theorem. So doing a problem is very simple as that. Almost like doing a problem in high school kind of things. Here, so verify, this is also a compulsory question in most of the examinations wherever this topic is there in the syllabus. So verify Cayley-Hamilton theorem for the matrix A, where A is this, and hence find A inverse and also something character, whatever it is. So basically verification of Cayley-Hamilton theorem, from that finding A inverse, not finding A inverse by using some other means. We know many methods to find A inverse, but here it is from the Cayley-Hamilton theorem we have to find the A inverse. So very simple. So first we have to find its characteristic equation, that of A minus lambda equal to 0. So this is the A minus lambda equal to 0. So this is characteristic equation. If we expand, we'll get the characteristic equation. So I am not explaining this, it may be boring again. So if we expand this, we'll get. So this, what is this expression? What is this called as? So this is characteristic equation of the given matrix, right? Okay. So now to verify Cayley-Hamilton theorem, what we have to say, what Cayley-Hamilton theorem says, the matrix A satisfies its characteristic equation. That means in place of lambda, assume A minus A cube plus 6A square minus 9A plus 4I equal to 0. Right? If we prove that, that means A is satisfying its characteristic equation. That means Cayley-Hamilton theorem is proved. So very simple. Right? So in order to verify Cayley-Hamilton theorem, we have to prove A satisfies its characteristic equation, that is minus A cube plus 6A square minus 9A plus 4I equal to 0. So as I told, is a school math. So A is there, we have to find A square, A into A. Right? So A square is there, we have to find A cube. So we got A square, A cube. So plug in all the values here. Right? So minus A cube value plus 6A square minus 9A plus 4 into I, right? As shown here. So A cube minus A plus 6A square minus 9A plus 4I equal to 0. If you simplify, so it will get this. That means 0. So that means that is proved. Therefore, what we say is A satisfied its characteristic equation. That means Cayley-Hamilton theorem is verified. So this is a common question. Right? So next is find A inverse, right? Not by using any other method. So by using this outcome, we have to find the A inverse. So from Cayley-Hamilton theorem, we are getting this, right? Minus A cube plus 6A square minus 9A plus 4I equal to 0. So where we know a cube, a square, a everything we know. So by using those values, by using this relation, we have to find a inverse. Very simple. So pre-multiply this relation by a inverse. Then what happens? This becomes a square, this becomes a, this becomes I, this becomes a inverse. That means minus a square plus 6a minus 9i plus 4i a inverse equal to 0. For I A inverse is nothing but 4 A inverse. I into A inverse is nothing but A inverse. So from this we can have A inverse, right? That is what they are looking for. So A inverse equal to, so 1 by 4 A square minus 6A plus 9A. So we had all these values, right? In the previous step we got A inverse, A square, right? So we had A square, we had A, everything we had. So if we substitute all the values, we'll get this. So this is how we use Cayley-Hamilton theorem to find its inverse. Okay. Now I think one more question they ask, right? That is find its characteristic roots. I think you can try it. So once we had a characteristic equation that is actually nothing but a separate problem, like we had this equation, we have to solve this for lambda values. Once the lambda values are there, we have to find corresponding x values. That is nothing but is a problem like eigenvalues and eigenvectors. So that is the brief discussion related to the two very important topic, that is eigenvalues and eigenvectors, and as well as Cayley-Hamilton theorem. So to summarize it, so what we have to remember is what is eigenvalue and what is eigenvector. Sometimes definition also they may ask. So there is a matrix A, there is a column vector, column matrix X, and there is a scalar A lambda such that Ax equal to lambda X. Then lambda is called as eigenvalue of X, A, and X is called as corresponding eigenvector. That is. And so how to find eigenvalues, eigenvectors? So first we have to find that A minus lambda I equal to 0. So which is called as characteristic equation. So if we expand, we'll get a polynomial. Then solving this, we get lambda values. Whenever we have lambda values, then we have to find corresponding x values. So depends on the order of the matrix. If order is 3, then we'll have 3 eigenvalues. We have to find 3 eigenvectors, unless until it is a repeated eigenvalue. So then all multiplicities, algebraic multiplicity as well as geometric multiplicity. Next follows Cayley-Hamilton theorem. So proof is also important, and also most of the times whenever a problem is given, numerical is given, verify Cayley-Hamilton theorem and hence find its inverse. Right? So finding the A inverse with the help of Cayley-Hamilton theorem. So that is this is the summary of what we discussed. Maybe in the next class we'll continue the discussion related to eigenvalues and eigenvectors with some properties related. So where it is very essential to discuss the properties of eigenvalues, eigenvectors with proofs or related logic behind it. Because in most of the examinations they ask as many properties, they state the property and they will ask us to prove the property. Right? So that's why this is important. We'll continue the discussion in the next session. So thank you.